Hello, everybody, and thank you for coming in. Everybody on Zoom, can you hear me?
Yeah, we can hear you.
Okay. So I'm Chahat. I've been working at University of Maryland on developing small, tiny robots, which are fully autonomous and which are at the scale of size of your palm. So this is my thesis defense, which talks about minimal perception to enable robot autonomy on research constrained robots. The first question in mind that comes in, what is perception? So whenever we talk about perception, we see this image where the robot sees a world in 3D and each pixel represents a part of a section. That means that you can see a refrigerator, Coca-Cola, and things like that. But why is perception a huge problem in research constrained autonomy? And everybody who's sitting here, there are more chairs, you can sit here. Move the chairs over there. So the three major problems are we have memory constraints, we have constraint in sensing quality and the amount of sensors, and the third is power. This is basically due to two main reasons. One is size, and the second one is the weight. So we can use nature as a blueprint because we have a lot of organisms from a single cell organism all the way to a blue whale, right? But they are doing the same task, but in a very different way. So we can see flies, bees, dragonflies, hummingbirds, and all the way going to cats and bald eagles. And this is a general trend that if your body size increases, your perception capabilities or the capability to understand the environment also increases. But there are few anomalies, such as jumping spider and cuttlefish, and they are doing things in a very different way. And we will be specifically talking about how these animals, being that small, are able to perform such a complicated task. So this thesis talks about going from this size of the drone from right to left, all the way to 120 millimeter, which is the size of the hummingbird. And in the green bubbles is what this thesis proposes, that you can achieve that complex perception capabilities while also decreasing the size. And this is what this question is, that how do we enable autonomy at these small scales? But the first question is, why do we want these small robots? So they are safer, they are more agile, and they can go through narrow spaces, as well as they are scalable, which is because they're cheaper as well. Next question is, why don't we have small robots and do all the processing off-board or on a companion PC using Wi-Fi? So this gives security if everything is on board, because you are not communicating from that drone to anything else. Second is you have a very robust system, and you can deploy them in the wild where you cannot take a huge computer. So next question I want to ask is, what is the optimal size? So there have been the other spectrum of research where researchers have been developing these tiny drones, which are as small as a penny. And the other side of the coin is where we have been working on research-grade autonomous drones, which are huge, so ranging from around 200 to 300 millimeter at least. So what is the optimal size where we can achieve the onboard autonomy as well as have a very small size? So this is the true size comparison, and it's only a fraction of the size. Just to put in perspective, the size of the robot itself is less than half of the length of the propeller of the bigger drone. So what is the smallest physical scale that is achievable for robot autonomy? So I'm going to present two robots in this thesis, which are able to do autonomous tasks such as navigation in unknown scenario on both ground and aerial domain, which are smaller than a credit card. So one thing we can learn from nature is that they have spent 3.8 billion years of research and development. So if you think of a hummingbird spanning from 120 millimeter, weighing a quarter of a kilogram, and having more than 1 billion of neurons, they are doing the same task as a bee which have less than 1,000 times the weight of the brain as compared to hummingbird. So how are they doing this, right? So if you want to compare these two beings, how are they different, and how do they tackle the problem of flying through unknown gaps? So if we see an eagle or a sparrowhawk in this case, they are going through unknown obstacle very seamlessly because they have a large amount of neurons and amazing sensors. But if you put in the perspective of a honeybee, which has a very bad sensing quality as well as fewer number of neurons, they are approaching the problem in a very different way by looking around the scene. So one thing is a fact. This is an image from a book called Mind of the Bee, that if the bee is presented in front of two different gaps or two different sizes, the amount of motion they have to do in order to solve or in order to traverse through these gaps varies with the size of the gap. So bees do not understand true depth, but they do understand the size of the gap with respect to their body length. So from that, we started, this is the work at the end of my master's at University of Maryland, where we developed a system which mimics the bee, which sees the scene from multiple views and compute optical flow, which is a well-known quantity in computer vision. That basically means the motion signature of how things are moving around. And you can use that to find these unknown shaped gaps and traverse through. Now, the reason I'm talking about the master's research is it had two major drawbacks. One, we will never know if the drone has traversed through because it does not understand true metric depth. It just knows that the part of the gap is nearer and the other part is farther away. It does not know if it has traveled 1 meter or 2 meters. It knows it has traveled 1 unit. So you will never know if you have traversed through the gap. Second problem it faces that you will never know if the gap is big enough. It will find the gap, it will try to go through. The gap might be too small for the drone to go through, but it'll still try. So these are the two major gaps. And I want to state this as an exhibit A, and we will come back to this at the end of this thesis. So from this, let me introduce the minimal perception framework, which talks about how we understand these two different beings and come up with a framework. And this framework is divided into three major sections. One is minimalism in terms of information modeling. Second is minimalism in terms of sensing modality. And third is minimalism in terms of data acquisition. So the first aspect talks about the information, right? So the first question is, what kind of information should I extract from the scene? And what is that minimum quantity that I need to extract in order to solve a problem at given task? Second question is, can I do something in a very minimal way to learn the scene structure rather than learning thousands of different textures? And in terms of minimal acquisition, there are two different ways to do it. You can add an active element, which is something moving in front of a sensor, or add a passive element in front of a sensor. And this is a part of the future work, which I'll be talking in details at the list in the last. The first part is minimum information models. So the question, this comes from Professor Yanis's work in 2016. He asked this question that what is the minimum information that is required to solve a given task? And I never knew that this would become a huge foundation of my thesis. So do not get confused this as quantization or compression techniques that people use. The question we are asking is, what do we need to compute in order to solve this task, right? So the first thing is, by observing scenes from a single image gives you texture. Like if you want to understand how mountain look like, you would need to get like thousands of these textures in order to recognize that's a mountain. Versus if you observe the scene from multiple views, you get the 3D information. You get the geometry and the structure of the scene. And this is how you can minimize network architectures rather than recognizing thousands and thousands of objects. You can learn the structure or learn geometrical quantities by motion. So let me show you a simple example. Like, what are the problems with single images in robotics? So if I show you this image, this image as a whole. Can anybody find the hole in this image? Yeah. Where's the hole? Yeah. How big do you think is right? Okay. Yeah. Okay. So the hole is this big. Okay. So the problem is, like, visually it is impossible to tell if there's a hole. But if I show you a video, it becomes very trivial where the hole is. Right. So these unknowns seem that you can not learn everything in the world for a robot. Robot will have to investigate in scenarios which it have never seen before. So to have a more generalizability in your system, we need to observe the scene from multiple views. So the moral of the story here is passive computing is this in 2023 is the output of neural networks which are still struggling to distinguish between food and an image of a dog. So these approaches are not the best solution for robots. So in terms of information modeling, what kind of quantity should I predict them? But first question is, should I even trust my data? So this is an example that we were working on to dodge a drone on a moving robot. So given an input image, we use the state-of-the-art, a huge neural network model to estimate depth. And this is what it gave. This is a result of Midas by Intel. So yellow means close and navy means farther away. If you focus on my body, you will see that my torso and my legs are not at the same distance, right? So should I be worrying about what I'm wearing that day in order to estimate depth, or should I be more creative and get a better information out from multiple views? So I should not wear this to get these things. So the amount of uncertainty that it leads today reminds me of a quote by Socrates that the true wisdom is in knowing that you know nothing. So just talking about uncertainty and what literature holds till date is there are two kinds of uncertainty. One is aleatoric and the other one is epistemic. The aleatoric uncertainty talks about inherent biases that it has in the way the sensor collects the information or collects the data. And the epistemic talks about and has inherent biases in the scenarios it will work on. Right. So we are gonna have a more generalized approach where we only want to talk about data, and we are going to focus this work on aleatoric uncertainty. So people have been developing systems with aleatoric uncertainty, where what they do is, given an RGB image or a standard image, they compute a quantity, it may be depth, it may be surface normal, and they compute uncertainty in these quantities, and then use that uncertainty to refine these data, such as surface normals. But what we ask in this work is only computing uncertainty enough? So here we present Ajna, which means intuition or third eye, and a framework for a generalized deep uncertainty formulation and how we can use that in robotics today. So just a bit of math. So the idea is we want to minimize a quantity, which is any prediction, which can be optical flow, stereo, surface normals, semantic segmentation, and things like that. And what I want is to have a penalty, which can be given as a regularizer, which can be given as lambda g of our uncertainty function. The idea is this function g is monotonic. Okay, that's the key. And h is a function which is also monotonous, but has the inverse nature of monotonicity. That means if g is an increasing function, h will always be a decreasing function, right? If we follow this rule, and if you want to minimize this quantity, and just plugging in the values of h, g, and lambda, we get all these papers from the last 5 years. So this is a generalized equation, a generalized form of computing any uncertainty for any kind of task like semantic segmentation, monocular depth, optical flow, and things like that. Right? So how can we use that just using uncertainty how can we compute or solve the problem of dodging, navigation, flying through gaps, and segmentation? So this drone is equipped with a front-facing camera, which is seeing all the obstacles, and then you see what it computes as uncertainty. And based on that uncertainty, we have a control policy that it dodges these obstacles. Next is dodging dynamic obstacles. Like there's a drone which is intruding, coming in the way, and you compute uncertainty, and it dodges that using a simple proportional integrated derivative controller. And the third one is flying through gaps that we saw in the first paper as well. That can be computed just using uncertainty in optical flow rather than actually computing the entire optical flow. Okay. So if you want to compare the results of dodging with existing methods, which is a hardware solution, which is Intel D435i, which gives you depth maps. The Intel Midas, which are huge neural networks that can compute monocular depth from one single view. And the fifth one is occlusion mask, which is a paper from Microsoft that gives you occlusion from two different views. And this is our results from Ajna that can directly compute the fastest moving object in the scene. So if you see that the more motion blur you have in the scene, the better the uncertainty gets, because this is the area which you are most uncertain for. Right? Then we have some simulated results there. We are flying through like realistic or photorealistic forest. And if we focus on the image ENG, there should be a branch that is missing in the largest neural network model that uses a single image to estimate it, right? We don't want this to be deployed in the wild. Versus a small 10 megabyte model that is observing the same scene from two different views is able to estimate these branches.
Why is Midas missing that branch?
Because so this scene is a simulated scene. It has not seen this specific rendered scene at all.
Is it because the branch is low on the tree?
The branch
is higher.
Even if branches are high, it will or may miss the branches unless you train the Midas on this specific data.
Can you also explain what quantities you compute?
So these quantities, yes. So everything we're talking about Ajna is computing uncertainty in optical flow. Last one is flying through unknown shape gap, where you can see similar results that Midas fails to estimate. So C4 and C5 are results from Midas small and larger network. It fails to estimate the gap, which is a very random shape, right? Versus if I give you something that is occasionally found in the wild, Midas D5 seems to observe and detect the gap, right? So should we be relying on single images in a more structured format, or what do we do in very unstructured or unknown scene? And observing the things from two different views is the key. Okay, so the idea is if you want to predict minimal quantities, you want to solve the problem through uncertainty estimation, right? But next question I want to ask is, what else can we obtain with minimal prior knowledge? Let's talk about segmentation. Researchers and in general people have been misleading the definition of segmentation with recognition. They're two different terms. Segmentation means one object is one object, second is the other object. Recognition means that you want to put labels on these objects. So object A is a glass, object B is a cup. That is what recognition is. Segmentation just says that these two are different objects. So we are looking for the problem of segmentation without ever learning on any segmentation data set. So this is the problem of segmentation. If you have a given scene, you want to put bounding boxes or mask on these set of objects. And you want to do that on alien or zero shot or never before seen objects. So if I ask you a question, this is a very weird object, which is a grass moss, which is kind of a rock. So if I ask you this question, can you identify this object on this given scene? Can anyone? Just for reference, I'll just put that photo here again. Okay, the answer is that's not even there. Okay, so it becomes almost impossible for objects which are looking very similar to recognize, right? So the fundamental thing that we as children learn is the art of segmentation by interaction. So this is a toy that kids are use these toys to develop the motor control skills with respect to the vision early in the days, right? So this is the idea of interactive perception, that we want to interact with the environment to find the hidden information. So I want to present NUTSEG, which is zero-shot object segmentation by repetitive physical interaction. So this network has never learned how to segment objects. It uses motion cues by interaction in order to find what object is different from the other object. So we use different modalities of motion robots, from using a manipulator or a drone to move the objects around. And even in scenes like this, we pick something and move the entire scene, and we get motion cues or motion signature from optical flow. And so the color represents a direction, and you can see the color wheel on the top and right. And the intensity means that object moves way more than other objects, right? So if I just see a scene and start poking with the robot, you get first segmentation based on your clustering, based on a spatial clustering algorithm that is not just based on the distance, but also based on the magnitude and the angle of the optical flow. And you keep doing this repeatedly to refine your segmentation mask until you have your final segmentation. So this is a scene where we artificially glued two objects together. So the question we want to ask is it one object or two objects? If you pick one object, it's going to be like, we will get both the object, right? So if you poke these things, we will get intermediate and final segmentation. And it shows that if the objects are glued together, they will have similar motion signature, and they will give you one common segmentation. And you can try on rocks or any other given scene. Right? So this is everything. We can understand that all the learning involved here that we talked about, like optical flow, requires a lot of data. And today, everything really in day of AI is governed by data. So if you want to see the model of how the floating point operation or the computation complexity and how much computation you need in order to like find something versus years, right? It has been till pre-computing or GPU computing age. It was following the Moore's law, where it says that the floating point operation of flops are doubling every 24 months. But after the first AlexNet convolutional architecture, it started doubling every 3.4 months. And after these GPT models, it has been starting doubling every 2 months. So after GPU computing, we required a lot of data. Right? So there's a Moore's law for machine learning, which says that the amount of rain data is doubling every 18 months. This is a quote from Denny Lang, the researcher at Unity. So just following this, there is a dire need of creating a scalable data that uses only open source maps and models. And you want to do this automatically. You don't want any person or anybody to manually either annotate these self-driving car datasets or manually do 3D modeling of these scenes, which is the case today, right? So here we present WorldGen, which is a large-scale generative simulator that can generate these scenes automatically using open source scenes, from self-driving views to drone views to objects that are moving around. and object fragmentation and things like that. So what it uses is we have an asset loader that uses OpenStreetMaps or Google Maps and uses 3D objects that are also open source and combine that with appropriate textures and lighting condition. And based on that, you can either systematically generate a city scenes, object fragmentations, object piles, and things like that. And we have a system in Blender that uses the dynamic lighting and camera formulation in order to have a photorealistic scene. And then you have a rendered high quality output that will give you all the annotations in the world. So this was the problem before, like you have to manually annotate, either manually create the 3D models to have that in simulation or manually annotate. So scalability was not available at that time. And this is what we use for the maps. So we have created the world. So why not just use that to automatically create the data set? So we can create from Google Maps and use semantic information to get terrain and depth maps, use that as semantics and put appropriate texture. And we get an amazing drone view from that. And all the way from the drone view, because we have the flexibility of 3D model, we can get to the self-driving car view. And this is a replica of a street that is in San Francisco. And you can change the day, lighting conditions, and even textures. And you can create any cities. So we have like Washington, DC, and we have Zurich and other cities as well. And this photorealism or photorealistic scene. So before this, there was a work from Kubrick that did not have all these photorealism, like motion blur, camera properties, and things like that. We included that to get a better understanding, to learn, to predict optical flow and depth models way better than what we had before. So just to summarize, data is useful for generalization, and we can create digital twins from these data. So on the left, you have a real city scene of San Francisco, and the right is exactly same spot in the Virgin simulator. You can create depth maps, semantics, optical flow, and things like that. Right. So that's the part of the Virgin. And next part I want to move is minimal sensing modality. So this is a traditional depth camera that everybody has seen. So this is an Intel D435i, which has an infrared or time of flight sensing, which can give you a depth map to metric units. So it will tell you if there's an object which is 1 meter away or 2 meter away, right? So this is what we propose, which is an RGB camera coupled with the super tiny or super sparse depth sensor that gives only 64 pixels. And this is the true size, which weighs way lesser and costs nothing as compared to D435i. So how do we achieve similar level of high resolution depth estimation from a super sparse data? The first question is, what can we obtain from the sparse depth? Yeah, so this is what we generally see, that you have an RGB image and this is what the depth will give you. Question is that we have a super sparse VL53 L5. So I'm just going to refer this as L5 sensor, okay, which gives you 64 pixels, that is only 8 cross 8 of depth information, right? So this is what it looks like, right? So if you look at each of these zones, they gather around, they gather a lot of intensity of light in about 5-degree field of view. And you will see a histogram, and it will only give you the mean of the histogram. So each of these pixels will represent only one value, right? So I'm going to present TinyDepth, which is generalized neural metric depth estimation method for palm-sized robots. So in this work, we presented how to estimate metric depth on as drones which is as small as pea-size, or like in terms of car which is smaller than a credit card, to estimate depth and to do navigation in the wild. So the key to this method is rather than observing the scene from one view that we talked about before, we want to observe the scene from two different views. So we get ground truth, and so this is how we train the network to estimate depth. So we see the scene from two different views, which will give you both RGB and ground truth depth. Okay, we use the ground truth depth to simulate how L5 should give us the value. We used an optical flow guided loss function in a standard convolution deconvolution network, followed by a upsampling layer, and that can help us to predict metric dense depth estimation. Right. So if you want to talk about results of the state-of-the-art paper that was just presented at the CVPR, so these are the inputs to the network. This is the ground truth. And this is the state-of-the-art method that is called Delta. That was the fourth row, which was presented this CVPR that utilize only single image. It works amazingly well on in-domain data set, but what happens if you have not seen the data? Right, this is how it looks like. But these are the scenes that are out of domain, not been trained, never been seen before, right? Versus the time depth model, which has not seen, performs way better. Delta uses one single
When
image.
you read the labels, they are not visible.
Yeah, that is a problem. That's what it's working on. So I can just reiterate the labels. So the first is RGB, second is VL5 sensors, third is the ground truth, fourth is the delta, which uses one single image, and the last one is tiny depth, which is our method. And tiny depth uses two images. So I'm going to have more comparisons. So I'm just going to talk about why not just use the L5 signals and over smooth that in order to estimate depth, right? So there are some results where it is achievable, but there are a lot of areas where that smoothing the L5 is not good enough for part of navigation purpose. So I'm going to compare this with minus. Note that the red method gives you metric depth. That means you know the metric unit, and the black ones are to scale. Right, so we have two models. One is tiny depth S, and the other one is tiny depth. The tiny depth S model works at 5 Hertz on a tiny Raspberry Pi. And we have results from gap flight, which has multiple gaps and unknown shape gaps. And so just to compare the L5, so if you just see these two parts, this one which is smoother now, these are not good inferences to estimate depth of the scene as compared to what we have in tiny depth, which recover the shape of the gap as well. Okay, so how do we use this to do navigation on tiny robots? So this is the robot car that we developed, which weighs about 100 grams and can be, so again, never been seen before scenes, like unknown scenarios. And it has a front-facing sensor setup that we first saw in the time depth, which is able to use this and navigate. So we use this as the same metric method to also estimate the gaps and to fly through. So this is the smallest robot, in my knowledge, that can fly through these small gaps today. So time depth to the rescue. So if you remember the exhibit A that we talked about, where the gap flight was not able to do these two tasks, which is not able to tell that if it has traversed through or if the gap is big enough. So now, because we get the metric depth on such a small scale, we can actually solve these problems. So note that because these sensors are so small, we achieve the depth sensing complexity in all the 4 faces of the robot. So you can see or estimate depth in all 4 directions. And rather than computing depth at every instance on all the 4 cameras, we used a basic attention mechanism in order to compute only on the face which is required. So you are getting the L5 signals in at all the 4 directions. And the closest direction, which is the nearest most direction, will be used to compute tiny depth. So you will be computing the depth models only where the objects are way closer. If you see an obstacle on the right hand side and it's able to see that and dodge. Right. So to summarize and to have a culmination of this thesis, I want to present Robo-beehive, which talks about how can we pollinate flowers in the wild. So this is the scale of the same scale of robot, which is 120 millimeter. So what we have is a Robo-beehive that carries these tiny small drones. So just like a mother bee or a beehive, it will go and the bigger one will latch on the tree. And just to put in perspective the scale of the robot. So the robot will go and latch, the mother beehive will go and latch itself on a tree. And then it will spawn these tiny robots from the beehive, and it will start continuing. Once it does that, it will search for flowers which has a front-facing as well as a bottom-facing camera. And once you have that, you go close, and in order to find the flowers, and you have a Velcro on the bottom in order to extract these flowers from the ground. But in the wild, you may also encounter these wild dynamic obstacles. And because we have a time depth model which can estimate it, which is front facing in all directions, we can estimate their trajectory in order to be safe from these agents. And this is how the flower detection from the bottom facing camera will look like. And once it has dodged these dynamic birds, it will go and pollinate and complete the pollination process. Okay, so I want to conclude till what we have is we want to rethink the entire robots from ground up if you want to talk about the size of robots which are as small as a credit card, right? All the way from the cognition level to the sensor level. We want to develop working on minimalist perception framework, which is not generic, but very task specific. So what kind of things you want to do, we have to build the framework for that specific robot and not develop a general robot. Learning structures rather than the texture by observing the scene from multiple views is the key for generalization. And we have to think the robots as embodied agents in order to tackle the problem as a very synergistic hardware and software codesign. So let me talk about the future work, where we talked about how we want to add elements in front of sensor. So one way to add is to have a moving or an active element, which can be by deploying rotating structures, which can be anything from an optical disc or a polarization filter, or by adding passive elements, which is something that we have seen a lot in nature. Like a lot of beings have different eyes, like human eyes are circle, but we have seen vertical, horizontal, and even cuttlefish eyes, and which will give you different, this is a scene of an LED, which is seen from different distances. But if you see that through a neuromorphic camera with coded aperture, you can get a free segmentation on how far these objects are. Also, by adding multispectral sensing, we can do a selective segmentation on hardware itself. Just like bees, like they are able to detect these flowers based on ultraviolet light. So by using these kind of filters, we can make this segmentation of finding flowers way faster. So this is an image of what bees would see. And I want to extend the tiny depth for dodging dynamic obstacles. So currently the problem we have is the hardware of the sparse depth sensor only works at 15 Hertz, which is not enough for these sensors to do dynamic obstacle avoidance. And these are the list of contribution over past 10 years. And I want to thank to all the sponsors and the media who have made this, and all the fellowships that have made this thesis and this research possible. And a huge thank to Professor Yanis and Dr. Cornelia, because they have they have kept me like a child away from home over the past 7 years, for 2 years of master's and 5 years of PhD. Professor David Escaramuza and Guido, who have helped me throughout the papers in the last 5 years. And Professor Fekau and Professor Chris Metzler, to introducing me to both active and passive or computational imaging, to neuromorphic and robotics in general. And Professor Nitin Sanket for being a huge part of my journey during my PhD and during my master's and my PhD. You will be always in debt to everybody that has worked in PhD. So we have a huge PhD family where people have been working together, irrespective of if the paper is there or not. Just we've been helping a lot, and I can't thank the entire PhD family and all the master students that have been working with me in the last 5-6 years. And the specific thanks to undergrads who have taught me the skill of mentorship and what it takes to mentor undergrads. So what's next? I'll be starting as a postdoc researcher at the Maryland Robotics Center with Professor Yanis Alumnus and Pratap Tokekar to extend this work on swarms. And thank you for your attention.
Thank you, Chahat, for this beautiful talk
Thank you.
and the beautiful slides.